Okay, so if it's not, we continuing. The last time we already done. Okay, let's see. We're already talking about the op-amp. Okay, and basically they get a true input and true output. However, right now you're looking only one output. That's what they're using, only one. They call a single-ended output. So if you apply signal into one input, another route is okay, and that one should be okay. However, when you apply two input to the signal, then they must be opposite. Okay, they have to be off phase. Okay, so the next one we're talking about 741 op-amp. Normally, in the op-amp, you get the current at the negative input, current at the positive input in here. It's supposed to be a 0, and the output supposed to be 0. However, sometimes they're not 0. They can be 1 millivolt. In this case, we're talking about the offset voltage. Normally, input positive, input negative, 0, then output have to be 0. However, if they not, that means the output be, you get the voltage they call an offset voltage. And now if you see on pin number 1, okay, they connect to the resistor here and go to pin number 5. So when you adjust this resistor here, that means you want to adjust for the offset voltage. Okay, so pin negative, pin positive around, output supposed to be 0. If they're not 0, then they connect pin 1 and pin 5, okay, to the port. You adjust that, try to make sure output to be 0. They say adjust the offset voltage, okay? Connect the variable resistor to pin 1 and pin 5. Connect both input op-amp to the ground. Adjust the port until Vout closes to 0. Okay, they're telling you input positive, input negative, ground, output supposed to be ground. If it's not, then they need to adjust the port until output to be 0. That's what they want. So that's why when you're looking into this slide, you understand what they want to do, okay? They want to adjust the resistor here until output to be 0. No more offset. Now, on that one here, they're telling you, you get a 1, not connect anything. That's what you get the gain. And the gain AOL. AOL means open loop gain. And that will be equal V out divided to V in. However, in this example, in this one, what V in basically, what V in supposed to be?
Close to 0.
The thing is sometimes the different textbook, they're using a different way. So that's why if you understand, then when you read it, you can follow it. What V in equal.
It
Who can
doesn't
tell?
have, it doesn't have a feedback resistor, so should it be 0?
Now I have to asking for what they equal first,
Oh, I see.
the formula. I'm not using V in. I'm using a different. So if you can answer my question.
So it's the gain times V out?
It's
No,
V.
that is already.
It's V plus minus V minus.
Exactly. That's what I asking for. V in equal V at the positive minus V at the negative. And that's what you say. Normally you call V VD, right? VD means the differential, different input between input positive and input negative of the op-amp. So in this example here, V in supposed to be VD. Okay, now, normally what VD they wanted. Equal what?
0?
Now what VD equal?
This is still open loop gain, Mr. Pham?
Right now we're still in the open loop gain.
Okay.
So normally they will be get the VD equal what? Okay, they normally will be equal. Zero. Remember that. VD equal VS input positive minus VS input negative. And they want it to be equal 0. Okay, so that means what?
V out should be 0.
Now VD equal VS positive minus VS negative. That means they telling you VS positive equal VS negative. That's the key point for you to understand it later on. Every time the difference between two input will be equal 0. If they equal 0, that means the V at positive equal V at the negative. Okay? And normally the gain, okay, AOL, AOL means the open loop gain without any connection. And they will be equal V out divide VD. Okay? And then we already at the basic, we already telling you. This is the circuitry. Okay? With the resistor RF and RI. So they not no longer up open loop gain. So then you can get a gain they call a closed loop gain. Okay? When they get a connection and they get the gain will be ACL, closed loop gain. Okay? And we go into that. Now, see how much, how many people can understand this, the display? Okay, data point right here. What's the name?
Is that the saturation point?
Now,
We got mid-range.
what? The gain, right? But the gain in here, you can see the gain in here. 0, 40, 60, keep going. But the space only at this point here.
Is it 100 decibels?
Yeah, 100 number. However, this point we call a critical frequency, right? You can see right here. They
Yeah.
going down 3 dB. So at this point, the frequency will be a critical frequency or cutoff frequency. And you're going down. What the frequency they equal?
Critical frequency. Yeah.
Equal what? You understand on this is a frequency
10.
domain, 10 hertz.
Mm.
Okay? They not put in here, but basically that will be hertz. Okay, frequency domain, not a time domain. So that will be telling you for the open loop gain. That means the op-amp not connect anything. And the cutoff frequency will be equal 10 hertz. Okay? That's what they already telling you right here. Critical frequency, 10 hertz. And my question is what the bandwidth for that one? What is the bandwidth?
Is it 10?
10 hertz. All right. That means from here to here, that's what we call a bandwidth.
And Mr. Pham, let me ask you something. Why do they have, it starts off at 10 to the minus 1.
That's supposed to be 0.
Oh, so the 0 is supposed to be over. Everything should be shifted over to the left.
Right.
Okay.
Based off of negative 3 decibels.
3707, turn right, Charlie.
Okay.
Mr. Fan,
Yeah.
could you explain that negative 3 decibel in reference to what Mr. Smith was saying? Why it starts at -1?
Okay. Let's see. 0 dB. They suppose 0, that will be 120 number. 20, 0, and the frequency supposed to be 0. Okay.
Hey, Lowell, I think what Mr. Pham is saying.
Yeah, if they said if I said, you can see that at a 0 gain, then basically frequency is supposed to be 0.
In other words, where it's got 10 to the -1, that's a mistake. It should start off at 10 to the 0.
Now, cannot 10 to the 0. 10 power of 0 mean equal 1.
Well, why does it start off at 10 to the -1 then?
Now, many they just using a -1 guarantee they 0 there.
10-0, is 10-0 considered to be center frequency or carrier?
That's a frequency.
Is 10-0 considered to be the middle,
One hertz.
the middle measurement of carrier frequency though, of the center frequency?
What do you mean a center frequency? Okay, now I can tell you one thing.
0.
0 here. Okay. Basically, that will be 0 hertz. That's supposed to be 0 hertz right here. However, they're using the power. 10 power of 0 mean 1. This is a 1 hertz. You see that?
Yeah.
That is 10. So this has to be 0. So they cannot using 10 power of 0. So that's why they're using 10 power of -1. Therefore, equivalent to 0 hertz.
0.1 is the 10.
If you said at this point here, you put 10 power of 1, it's wrong.
Yeah.
The thing is 10 power of 1 equals 1 hertz. That's why they put out right here. 10 power of 0, 1 hertz. 10 power of 1, 10 hertz. And 100 hertz, and so on. So that this one is supposed to be 0. However, they want to using the power of 10. That's why they put 10 power of -1. Equivalent to 0.
But is equivalent 0.1.
Can you say again?
This point look like a 0.1 because it's 10 to -1.
10 power of -1, what you get?
This is 0.1.
Is it equal 1?
0.1,
Okay,
1/10.
that doesn't matter. You don't care about 10 -1. Basically, they want that to be 0. Only thing is they're using the 10 power. So at this point, they cannot put up 10 power of 1. The thing is, basically, they want it to be a 0 hertz. So that's why they put 10 -1. This is a 10 power of 0 right here. That equals 1. That doesn't matter. Who care on that? Only thing is when you're looking into this right here. Yeah, go ahead.
Beginning of the cycle, everything is at 0.
The thing is that the frequency domain hertz. Then you have to be start from 0 hertz. And you can say 1 hertz in here. Instead, you have to using just a number. But they like to using the 10 power. That's why they put a 10 power by that one here. That it means nothing to me.
All you're really saying, Mr. Pham, is I get what you're saying now. 10 to the negative 1 is so small. It's so small that it's almost 0 anyway. So they use it as 0.
Yeah, but they're supposed to do that.
It's
They're
just on,
supposed to put a 0 here.
it's
Right.
on,
1, 10, 100,
Right.
1,000.
it's on a 10th scale.
But we don't care on that thing. Now,
Logarithmic scale, right?
one thing I make sure you understand, the bandwidth for the open loop, they going from 0 up to 10 hertz. Is that right?
Right.
That's the bandwidth. And you cannot do anything with that kind of the bandwidth. Okay?
Question, Mr. Friend.
Yeah.
Between 10-0 and 10-1, that square space, meaning in the voltage gain in decibel, it's 0 to 20, you have a square. So what is in that square that has a specific division property? Is there a division property in the 10 to the 0, 10 to the 1 box up to 20 decibel? Is there a grid?
No,
No, there's no
No.
gridded division.
don't go too much thing confusing.
Right,
Only thing what I'm saying here, this is a 1 hertz. You see that 10 power of 0 mean 1.
Right.
This is a 10 hertz. And this is 100 hertz. That's it. Nothing, too many things going on in that 10 power of 0 or 10 power of 1. That doesn't matter. Only thing, I make sure you understand the bandwidth, they will be how many hertz?
10.
10 hertz. And you cannot do anything with 10 hertz bandwidth. Okay?
This is a logarithmic scale, right?
Okay. The bandwidth for the open loop gain only 10. So now, if you want to increase more bandwidth, okay, that means to make the bandwidth wider. And now you can see this line here. Okay. They say operational amplifier open loop gain. Okay. So now at this point here, what the bandwidth?
It's 100 hertz.
100, yeah.
100 hertz right here. Okay. They're telling you, you reduce the gain from 100 to 80. Now you increase the bandwidth. You see that? And then keep going. Okay. At this point right here, okay, you get the gain equal 40. They keep going down. However, the bandwidth now will be what?
Bandwidth is, what,
10,000.
10,000.
10,000 hertz. Okay. And now when you reach to this point right here, okay, the gain is 0. Okay. And what the bandwidth?
1 megahertz.
1 minute.
1 meg.
1 megahertz. That's what they call a unity gain. Okay. For open amplifier. So basically you cannot do anything with open amplifier. The reason the gain they get only 10 hertz, cannot do anything. Now,
And Mr. Pham, before you leave that one question, on your chart there, it says slope equal minus dB, 20 dB per decade. So shouldn't that minus 20 dB be where 100 kHz is at, not where the arrow is pointing?
yeah, that means they just telling you at this point, okay, they going down 20 dB.
And yeah, but I'm saying well, it's maybe a typo, but the arrow should be where it says 10 to the 5th. That's where minus 20 dB is at, right? 10 to the 5th.
20.
No, it's a negative 20 slope
Yeah,
for the entire line.
yeah,
Oh, the entire line.
yeah.
Hey, thanks a lot, guys. Thanks a lot.
Sure.
Okay, negative 20 slope.
Okay, the first one we will be learning. That's what they call inverting operational amplifier. Okay, now you see that the amplifier here. Negative input, positive input, and that is the output. And they connect the RF. RF means the feedback resistor. That's what right here. Feedback resistor. Connect from the output back into the input here. Okay. And now this is the signal applied to the input of the op-amp. If the signal applied to the negative input, then they call a inverting amplifier. We already know negative inverting input, positive non-inverting. Okay, so if you reach here, you can see RF feedback resistor between output and inverting input to produce the closed loop gain ACL. So now you will be get the gain, but that gain not open loop, closed loop. Okay. AOL means open loop gain. ACL means closed loop gain. No current flow into the input terminal. That means you get the current flowing here, go to this point, and either they can go up, or they can go down, or they can go in. Now try to understand how they go. If you get the current flow here, so they can go in up, they can go in down, they can go in. So now, how come they not going into the op-amp?
Wait a minute, Mr. Pham. I get your current going up and current going down, but that last arrow that you drew, you're showing it going in, and it says no current flow into the input terminal.
Right.
Because
That's
having impedance.
That's what right here, current coming in, right?
So it goes to that point, but it doesn't actually go in.
Why? That's what I just want to ask you. Why they're not going in? You have to explain to me.
High
How-
impedance.
Well, it says a high input impedance.
Okay, that is the reason. They get a high input impedance. So that's why not current cannot coming in. And now, how come they not going down?
B1 and B2 is the same point.
Exactly. The thing is V at the positive and V at the negative equal. So that current cannot flow down. Okay? If you not agree with me, let me know. We already set at the beginning, VD function here, VD equal 0. That means V all the time, V at positive and a negative equal. So they're not going down. Okay?
Okay.
Okay, so now the current will be going up here and they going this way. So normally you get a positive here and negative here. Okay, my question is, at this point, what the voltage here?
0.
0,
Yeah,
right?
Yeah, zero.
How come they 0?
Virtual ground.
virtual, yeah.
Now, I want to know, you say on this point right here, you say 0 volt, I agree. But my question is how? How come 0?
VD,
V minus plus.
VD, V2 is equal to V1. And since V1 is grounded, V2 is basically equal to V1, which is 0.
Exactly. The thing is we're already telling you, V input 1 and V input 2 equal, right?
Right.
So this you connect the route on this one here, 0 volt, then this point also 0 volt. However, the difference is, on this point, route they get a different name. They go right here, virtual route. Okay, virtual route. That means route, however, current still flowing. So now what the difference between route here and route here? You get two route. This point, they get a name virtual route. Okay, and this also route. So this is route. What the name for this one?
That's like ground for everything, right?
Reference, yeah.
Okay, I asking the name. You say route, but what route?
Like the reference ground or something?
No,
Is common?
Common ground, yeah.
I agree with you. That's a common route, right?
Right.
However, I want a name.
Earth,
This one, they get a name.
It's
Virtual.
floating ground,
is it-
or it doesn't necessarily exist.
is it called Earth?
Okay.
Oh, physical ground. Come on, Mr. Bam, that's a
Hey,
word.
how come I still memorize and you guys don't?
You got 50 years in this.
It's only visual.
Okay, now what do you mean a physical route? Physical route means you need to connect the wire to the route, to the common.
The ground plane?
Yeah, the route point, you need the wire connect from input positive to the route. That's what they call physical route. However, this one 0 volt, but they not connect directly to the route. So that's why they get a different name is virtual route. They still route 0 volt. Okay.
One has, in other words, one has a connecting point and the other one does not.
Right. You must be able to connect the wire from positive to the route. So that's why they route. But
Okay.
this one, no. Even the 0. Okay. Also in here, they said the different input is 0. Okay. V1 equal V2. And the closed loop gain will be minus RF divided Rin. And now we prove for you. Okay, now. For this one here, okay, you get a 5 volt input connect to R1. Okay. And also the output, you can get a V out right here. And this is the load resistor, RL. So the first thing, you can say you get the current from 5 volt, go here. This is the current I. And this will be positive, and the other side will be negative. So this current going to the RF, and we already telling you, positive this side, negative this side.
Mhm.
So when this current coming down here, okay, so you can get either current go this way and current go down here, okay. Now, my question is, did I, when they go up to this point, how come they not going down? You see that on the picture.
Mhm.
Current I go here, go to this point. It's supposed to go down here. How they not?
Good question, Mr. Pham. On that virtual ground, if you have 0 volts, what's the minimum amount of current that will flow without the assistance of a voltage value? Is
That
there
doesn't matter, depending on what the current, any current can go in here.
any as high as possible without voltage?
Now that's what you have to looking for the specification of the op-amp, depending on what kind. 741 or different name. If you want to design anything, then you have to looking into the data sheet manufacturer of the company they build it.
So it's determined by the diode inside, right?
I don't know what inside. You know what inside here?
That's what I'm saying is your question is why doesn't it go down? So
No, that's different. My question is how come they not going down? Answer for me the right answer. This current you already know they going this way. And they go up to this point. How come they not going down?
Because the ground is more positive.
Exactly. That's what you understand. You can say on this side here, round means 0 volt. And this is a negative. That means they negative voltage. So the current must be flowing up from high potential to a low potential.
And Mr. Pham, I don't know if this makes sense or not. You see on your plus terminal, the plus terminal is at ground. So since the plus terminal is at ground, does it make the that plus where the load is at, is that why that,
Okay, now. You agree with me, this a negative.
correct?
So that negative, so that one right here have to be negative.
Right,
They just a wire.
yeah,
So you get a 0 volt for the round, okay? And now you get a negative here. I given you example, minus 5 volt. Then the current have to be flow this way, correct?
okay,
Current flow from a high potential to the low potential.
Yeah, 0 is
zero is higher than 1.
higher
I
than
mean,
Higher than
negative.
minor.
Minus,
minor.
yeah, yeah.
So this current go to this point, they not going down, they go into the op amp. You see the arrow
Mhm.
go into. And also you get a current from the load go into that one. They also go into. So now in this case, they call op amp sync current. What that mean? That will be telling you op amp will be pulled current into the op amp, syncing.
Yeah.
Okay.
So the op amp current is equal to LO plus, I
I
mean,
plus IL.
IL, yeah, right.
Okay. Okay, tell me what inside this symbol. Even we don't have to know, but I can ask you what you think what inside. Okay.
Probably transistors, capacitors,
Yeah,
resistors, just like we
Different.
studied.
that one. Okay, now. Oh, this is the one we don't have it. That's a differential amplifier inside. I already showed you on a differential amplifier.
Different amplifier, yeah.
Yeah, they just are inside. That's just a symbol. Okay, anyway. So in this case, op amp syncing the current. That means they pull the current in. Okay, that's what they call a sync current. Okay, now if I want to calculate the I, current I here, can you tell me what I equal?
5 volts divided by 1K.
5 volt divide 1K.
1K,
Correct. 5 milliamp.
so 5 milliamp, okay.
Is that right? Okay, if you don't understand, let me know. Try to make it clear for your guy. You understand, then you will be memorized. The thing is, how come I say I equal 5 volt divided to R1? What voltage here?
0.
0, right?
0 volt.
So you get a point, you get a 0 here. Ohm law. Then that's why I equal 5 volt divided to 1K. Okay. Now,
V-
what V out equal? What V out equal? Okay,
Is
V
it like a
out.
voltage divider or something?
Now, V out will be measured from the output to the route, right?
Right, over the load resistance.
I times R. Okay, V out equal I L
Using the gain.
time R L. Law, right?
Right,
However, you need to put a minus. Why?
because it's inverted.
The thing is, the voltage you measure from output here, okay? Output to the route, and the current flow opposite from route up. That means the voltage and the current not the same direction. So that's why you get a minus. Okay?
okay.
Now, also, I want to say, how come I get another formula for V out? I want using I. What formula?
Gain for input.
Okay, V out. Measure from output to the route. That means from here to here. And also can be from here to here. This is route also, right? Can you see that?
Right,
That's still the route. So V out you can see equal I times R F. Is it correct?
Yep.
Okay.
all right, Mr. Pham, can you explain that one more time?
V out means measure from output here to the route. This is to the route right here,
Right,
right?
right,
Also, this also route. So also the voltage from here to this point here. The thing is they route.
-2.
Exactly. The thing is current flowing this way. And the voltage measure go the other way. And also you can see right here, negative right here. So basically, they will be equal minus I times RF.
yeah, that's what I wanted to hear, okay.
That correct?
Yep.
Okay. What
So you're saying that it's minus 5 milliamps times 1.5 K?
yeah, I'm not substitute a value into it. I try to,
Okay, okay, okay.
okay?
All right, yes, sir.
Understand what's going on.
Okay,
We can substitute easy.
okay.
Okay, now we already calculate the I. Where I will be equal. We already calculated plus minus 5 volt. So I say this is V in. So they will be equal V in divide R1. Okay. And then you can substitute I into that formula. So V out. Okay, equal minus I don't want I using V in divide R1. Okay, time RF. Okay, so if I want the gain ACL, the ratio between V out divide V in. So if you take a V in going down here, okay, that means V in here going down here. So they can be equal minus RF divide R1. Okay, this is the formula for the closed loop gain of the inverting amplifier. Again, ACL will be equal minus RF divide to R1. Normally, you see in the textbook, they using RF. RF means feedback. Okay, they connect from the out to the in. That's what they call RF. However, at work you cannot see RF any RF. The thing is when we design the circuitry, we're using R1, R2, R3, R4, R5. Okay, if I get R10, the last one, I know in the circuit board I get 10 resistor. So in order to understand, you must understand that you're looking for any resistor connect from the output of the op-amp back into the virtual ground. That will be IF.
Hey, Mr.
So this is
Fairman,
completely proof for the gain. Yeah, go ahead, Mr. Smith.
yeah, it's no big deal. Just so everybody know where you got those 5 dots to the left. On the second one, it says ACL equal minus R2 over R1, but I think you use RF for R2. It's no big deal, just to let everybody know. ACL equal minus R2 over R1.
I understand what you say.
Yeah, so R2 and RF is the same thing. Yeah, exactly. Right.
Okay. Okay, now you do for me on that one.
I didn't know that was coming.
Quickly get it done. Just a few minutes to make sure you understand this configuration inverting amplifier. I said when you're looking into the circuitry, you know that the inverting amplifier. You don't have to prove anything, but they want you to do calculation, at least what they need.
Ten.
Okay, who get the answer? Let me know. 10, right?
Yep.
Number 2,
Is that 10 or minus 10?
gain not minor. Okay, let's see. To make it correction, the gain equal minus RF over R1.
So it would be minus, wouldn't it?
Right.
Yeah,
Right.
yeah, minus 10, yeah.
Minus 10. Thank you. V out.
And then the current would be,
Now, next number two. You already get the gate. You already get the input at 1 volt.
Yeah.
so
Minus
it's
10,
1 volt,
Minus 10.
is 1 volt times minus 10, right?
Exactly.
Yeah.
Correct?
Correct.
Now, current I.
Current I is 1 volt divided by 1K. So it's 1 milliamp.
Current I to R2. That means 1 volt divided to 1K. 1
1
milliamp.
milliamp. Yeah.
Load current.
That's where you get me. IL. This is IL.
It looks like it's also 1 million. Is that
1
right?
million, 1 million, yeah.
1 milliamp. So the current, the LO, that's the one that goes into the op amp, and it's a combination of the load and the I. So does anybody get 2 milliamps?
Add them up.
Right.
Okay.
Okay, so any question about inverting amplifier?
Can I ask just a question? Is the IL considered, is it negative 1 milliamp? Just because it's the opposite? Is that why you get to 2? Because the load going in, or
Okay,
excuse
now,
me, the
now.
amperage going in should be 2.
Okay, now. First thing I am telling you, the current never negative. Okay? If you draw the current this way, I equal 1 milliamp. Okay? They go this way. But if you say equal minus 1 milliamp, what that mean? That means the current have to be go this way. Okay? You never get the negative current. And now I prove it for you. Okay, I want to calculate the IL. Tell me the formula.
B0 over
IL equals, oh, IL. Okay, IL equals LO minus I.
It's
Now,
equal to V out divided by RL.
It's 0 minus V out over RL.
perfect. I talking about Ohm law. I go to register, that means the difference between this side and the other side.
Hey, Mr. Pham, can you use your pointer? Because I don't believe I saw.
Can you see that?
Yeah, go ahead.
That means the difference between here and here, right? Divide to the R5. When you calculate the voltage, the current through resistor, you have to calculate the difference between 2 points. So this point is ground, 0, right?
Right.
And minus V out. Then divide R low, R5. Is it that correct?
Yep.
So you got 0 minus
V
out
out.
divided by R5.
Okay, now 0. Minus V out will be minus V out.
Yep.
Divide R5. And that will be telling you minus to minus.
It's a plus.
So that's why the value will be 1 milliamp, not minus 1 milliamp. Current never negative. When you get a negative, only telling you current supposed to flowing from left to the right. And now they have to be from the right to the left. That's it.
Oh, I see what you're saying, because V out is going to be a negative.
Right. Okay, any question? Okay,
Mr. Pham,
yeah,
with just one real quick clarification. So what you said was there will never be a negative current.
correct.
There will never be a negative current flow, only a positive current flow, right?
Right, that's a conventional.
Conventional.
We're not talking about electron flowing. You deal with the conventional. Okay, finish for me this one. Example. Quickly, I want to get another important also amplifier. For the operational, the first one, the inverting amplifier. You must understand. And the second one will be non-inverting.
Its ACL should be 3,
So the closed loop gain
Minus
will
3.
be
minus 3.
Yeah. Minus
4.5
yeah.
by 1.5, right?
Yeah.
What you get?
Minus 3.
Minus 2,
3.
minus 3.
Yeah. 3.
V out.
Minus 3.6.
Okay, input at 1.2 volt peak to peak. And you take a 1.2 times 3, right?
Yes, minus 3.6.
No minus.
So it's 3.6.
3.6. Yeah.
Why I said now will be no minus?
It's just
You
peak to
said- you
peak.
said-
It's just peak to peak. So it's 3.6.
Peak to peak.
The thing is, this is the AC, not DC. AC, you can not get a negative. The thing is, they keep changing. Right?
Right,
So
Yeah.
that's why you get the absolute value. But DC, then you have to using the negative,
yeah, that's right, it'd be out.
but not AC. So current I to R1. You take 1.2 divide 1.5.
0.8 milliamps peak to peak.
Yeah. 0.8. 0.8.
0.8.
0.8 million.
Okay. So they will be telling you input here, output here. They will be opposite. Input going up, output going down. Input going down, output going up, 180 degrees of phase. So that is a two example. One for DC input and another one for AC input.
Hey, Mr. Pham, and then what you talked about the phase, so that's with respect to inverting, right?
Right.
So, all right, so, because if you ask the question, say, for example, on the test, then that's for inverting, not non-inverting.
They said they will be asking you what the output, input, output phase relation. Then the answer will be our phase.
Out of phase. Okay, all right, thank you.
Now, that's the one we try to get it done for today. Now, this circuitry they call a non-inverting amplifier. So, question, how come they call a non-inverting?
Because the input and the output are in phase.
Because the signal goes in to the positive instead of the negative.
Exactly. The reason is the signal now, they go into the positive. And the positive name non-invert, right?
Right,
The other one, they go to the negative. And negative will be invert. So that's why I said looking into the circuitry to recognize right away. Inverting or non-inverting. Okay, now the voltage here, VD equal what?
Zero.
is that same as,
Zero.
the same as before?
Exactly, on the time, VD equal 0. So that's what they talking to you right here. Okay, VD equal 0. So that means the voltage here and the voltage here will be the same, correct?
Yeah, the same.
Voltage at this point and voltage at this point must be the same. The 5 volt in here is not a input to the positive. Input to the positive, that means at this point right here. So we need to know on this point right here what the voltage equal.
2.5.
That voltage here. That means voltage divider, right?
Yeah.
I can say V 1 and that will be V2. Then V1 equal 5 times 1 divide 1 plus 1, 2.5. So this point here, 2.5 volt. You get that? Now telling me what voltage here.
2.5.
2.5.
Negative.
No. Why?
Are the same.
Same. 2.5 here and this one the same. 2.5. It's correct or not?
Because are you saying, Mr. Pham, because the voltage at V plus and then V minus is just, they both in, well, they both equal to 0. So if one equal 2.5, then the other one's got to equal 2.5.
They have to be equal.
Yeah,
Okay. What voltage here?
2.5.
2.5.
Correct?
Right.
Okay. So the current have to be flowing. Current have to be flowing from 2.5 to the route, correct?
Mhm.
Okay, this current basically coming out from here. Okay? Not from here. Not from here. The thing is they get the same potential, no current. So this current coming from op amp. I out here coming out. One go to the load, one go this way will be I, and I flow this way. Okay? And they go to this way, they cannot go down. They will be go to R1.
2.5 milliamp.
Okay? So basically, this is what they try to explain to you, but I don't care now. I want to try to make sure you understand what's going on. When you're looking into the circuitry, you can recognize what the current going out here. I out. One go up, one go down. In this case, they call op amp the source current. That means current from op amp going out. When they pull the current in, sink current. Okay, let's see.
So you said the source current, the sink current is in and the source current is out.
Exactly.
Okay.
Okay, now,
Wait, say it one more time. But pulled in is sink and
sink, they call it sink,
in is sink and out is source.
right?
Thank you.
Okay, now,
So just real quick question, Mr. Fan.
yeah,
So on the source current, that is technically returning back to the generator.
they're not going back to the generator.
Right, so if your signal's coming from someplace, that's considered your source, right?
Now, if they come out of the op-amp, cannot say someplace. They have to be coming out right here.
Right, so if the source current is returning from where it was generated from,
They generated from what the source right here.
it's only, but it's being generated technically from the 5 volts.
Yeah, from the 5 volt, but the 5 volt is not this way. But you have to get a 5 volt.
Right, all right, so after it's divided, it's only returning back to the
2.5.
2.5.
And now I already proved 2.5 here, you get 2.5 right here. You get 2.5 here, and this is a round current must be flowing this way. That's what I showed you right here. And this current will be the same on this current.
And technically it's it isn't a negative current. All right, it's going backwards. All right, thank you.
Hey, Mr. Pham, before we get off of this one, I want to piggyback on what Lowell was saying. So I want to work these out so I make sure I understand what's good. What I want to know is how much current is flowing through IL, how much current is flowing through RF, and how much current is flowing through R1 and R2 and R3, because this gets kind of confusing.
How much current? You must do your calculation when they given you the circuitry. Then you can see.
Your certificate, Joe.
Okay, now. First thing, what VL equal? Tell me the formula.
VL equal,
V-
when you, it says VRF plus VR1.
Okay, first thing I can see VL equal IL times RL, correct?
Yes.
And also VL equal
R1 plus RF times I.
okay, that means they equal the VRF. That means V across RF plus VR1, correct?
Yes.
VRF plus VR1. VRF equal I times RF. Plus I times R1. That's correct or not? That means they will be equal to voltage across this resistor adding voltage across R1. And that also get the same current I. Okay. And now I say I here. Okay. RF plus R1. Is it correct?
Yes.
Okay. So I equal
Factor now.
Okay, I equal VR1. Or if I can say right here, V2. Okay, and V1 or V2 still same thing. So that will be V1. Okay, I equal V1. Divide R1. Okay, and now I substitute I into this formula. So basically, I can get VL equal V1 divide R1 time RF plus R1. Okay, so now if you want to calculate the gain, ACL equal V out divide to V in. Okay, that means V1. So you can substitute, you can calculate that one. Okay, V out divide V1. That's what you come up with this formula right here. This is the gain of the inverted, non-inverted. 1 plus RF divide to R1. That's only thing you need. And the rest will be easy. If you want to calculate the V out, then V out equal ACL times V in. Remember, V in have to be here, not here. V in have to be right at the positive input. And if they want to calculate the I out, then you take a I out equal I plus IL. If you want IL here, you take the V out divide to RL. Okay, that's only telling you the gain of the non-inverting on the time must be higher than 1. The thing is 1 plus RF divide to R1. Okay, so I can stop it now for the guy to take the quiz today. Okay,
Okay,
Postpone the quiz till next week.
Sounds good.
normally 1 a week. However,
Mr. Pham, you just fried our brain.
hello, Sam.
Yes, Mr. Pham.
You ready?
Yes, sir.
Go ahead.
Okay.
That's only 80
So-
questions, so not take too long.
Okay, here we go. Okay, so we're gonna be okay. Can you all see that?
Yes.
Okay.
yep.
make sure you understand the question in the quiz here. They will be the same with the left volt unit test. So you want to get 100% unit test. And try to understand.
Okay, so that's pretty much it. So make sure you upload it into the website before 12 noon tomorrow, okay? All right, looks like pretty much that's done. Let me see what we have. Okay, so I don't see any chat or anything, so everybody's good?
Mr. Pham, can you post today's Zoom meeting online?
Appreciate.
What's that?
Okay, so any question? Otherwise, good
Yeah,
night, everyone.
can you post today's meeting?
I said we'll see. Take it out.
I'm sorry,
I said you just look into that and see.
You're gonna
what's
put the
going on.
video on the web. That's what he said.
I know. That's what I said. We'll
Okay.
speak on that. Take it out.
just to look for it.
Wait,
If you go into the web and you see it,
Okay, thank you.
okay? Good night, everyone.
Good night.
everyone.
See you guys next week.
Good night. Thank
Good
you.
night.
Bye.
Bye.